Hi, this is Ashishar Bedekar, and welcome to my podcast, The ARB Show. I'm thrilled to introduce today's guest, Bruce. Bruce is a highly experienced technologist and designer with rich background in AI and IoT. He leads initiatives in connected life, mobility, telecom, clean tech, with a focus on advancing us towards advanced general intelligence and singularity by 2030. Bruce specializes in real-time energy management, designing machine learning algorithms to optimize energy use and enhance smart home experiences. His great research in photonics, emotion tracking, brain-machine interface, and natural language drives innovation in human-machine communication through AR and VR. He's a serial entrepreneur, mentor, angel investor, and startup advisor, and he combines multitude of skills across telecom, wearable, IoT, and enterprise sector. He has his open perspective has been shared with involvement in 9 startups and active mentorship with organizations like Lition, Mosaic Venture Labs, Park Labs, SOSV, and he is a global respected voice on technology and entrepreneurship. And I'm really thankful for him to accept my invite. Thank you, Bruce, to be a guest on the show.
I think with all of that, I might as well just did I do all that? I don't think so.
Yeah. So really keen to hear your views, Bruce, on photonics and in semiconductor CPU and all optical networks. It's a fascinating topic. As I said, it's a new topic, and really keen, along with the audience, to hear more about it. Over to you, Bruce.
Well, I mean, if you think about the problem, all of us have been in computing for a long time. We all have PCs, and we all built PCs before. And when we used to build a PC, you put in your motherboard, you get your motherboard, put in your CPU, put in your memory, you put in your hard drive. But, there was a distance between all of them. And that causes latency, what we call latency, and it causes bandwidth issues. So as we get into these massive AI data centers, every millisecond counts. So how do we solve this main problem? And one of the main problems was the network. So if you think about the CPU, get your good Intel CPU, or that connects to a Ethernet physical interface, which is copper, and then that connects to a fiber converter, and then you stick in a fiber adapter, and that's how you go between your computer and the internet, or to the next computer. Well, the problem with that is you're going from electronics and to copper. You're creating heat, you're creating a delay, and then you're converting that into optical, and that creates a delay, and it creates a loss because you're going from a square signal to a round signal. So there's some issues there that have to be taken care of. We've been doing it for a long time, and we've accepted that minor loss, and that. But now that's not acceptable anymore. So now we've gone into putting. Originally, there were 2 companies, Intel and a European company, that actually tried to build the photonics, the laser, inside the chip, to try to grow it inside the CPU. Well, it turned out there was a lot of the heat and all was just too much for a CPU. So now what they do is they put it next to it, and what we call the substrate. So right next to that CPU, we come out electronically, but we go straight to the optics. So we don't need a DSP. We can get rid of the DSP chip, and we can go straight into the photonics. And now this was originally called PIC, Photonics and Integrated Circuits. Now it's called CPO, that's co-packaged optics, which is part of PIC. So PIC is a general term for the whole thing. But in the CPU part I just talked about, that is actually a CPO, which is we're co-packaging a chip and the photonics in one. So you'll see, instead of if you remember the old days, you used to plug in with these copper feet. Well, you'll still have those, but now you on the side, you're going to have some copper wires coming out, or copper streams coming out, and there'll be a little header for you to connect your optical to it, your connection. So you're going to get one for network, maybe one or two for network. You'll get one for memory, if you're going to go anywhere short memory. If you're going with like the NVIDIA chips, that memory's built in, but your hard drive may not be. So we can now go optical. And then what NVIDIA is doing with their NVLink, they're actually going computer to computer with optical. And trying to, that's the goal. Right now they're doing copper, and then they're moving on it to get into optical. Now, in short distance, copper is still better. And so you go copper to copper, forget the optical. But if you're going beyond 2 meters, well, yeah, you got to start thinking about optical. And, if you ever seen the design of, the NVIDIA rack, that's 72 computers looking like one. and we go way back, so that blows our minds when we think about that. But yeah, so photonics, there's a lot of work still to be done, and this co-packaging and getting the lasers smaller and more efficient and less heat, because lasers do create heat. So how do we manage that? So thermodynamics is still going to be something there's a lot of R&D for. That's where that is.
Yeah. So let's step back and try to explain this for a non semiconductor or a professional. So for a layman, would it be right to say that the analogy what you can explain is something like fiber optics, right? When you have got fiber to the home, you get better kind of signal, a better speed, because now everything's at the speed of light. If you contrast that with good old, dial-in telephone, internet, or based on copper.
Sing the song. Go ahead.
Exactly. So it's like that, but at a chip level. Is that analogy correct to explain it to a non-techie?
Yeah. So the electrons versus photons. So electrons can be noisy. They can lose them. So it is the reliability. So we're going at the speed of light, and not the speed of electricity. Light is faster, but electricity at a short distance is actually better. But in a long, beyond 2 meters, light travels faster. And it's very, very reliable. Now, let me explain the cool part of this. So you have seen that light is one color. And for the last 20 years in the data center business, we've been running multiple colors across the same cable. So we have a projector that projects multiple colors. It's called DWDM. And the receiving guy has a little receiver, and he looks for the different colors. He looks for the pulse. The pulse from light. So it's actually, if you were really, really good, and you could actually put through the light, and you can see it pulsing. And that's what it is. It's a wave pulse that sends the data to you. And so what we can do, the difference between Ethernet copper and Ethernet fiber is we can go up to 16 colors. So whatever the bandwidth, which is 25, we can get about 25 gig now, we can put multiple colors in. And now this is how we get to where optical is currently at about 800 gigabits per second, going to 1.6 terabits per second. Okay, so in our day, we used to have a 300 baud modem, and then when we got to 1200 baud, we were too cool. But this is 1,000 times more, maybe 1,000 or plus, maybe 10,000 more. But so we've gone from very unreliable analog signal to electrical pulses to optical, and the optical is at long distances. It's very, very reliable, and it gives you, speed, reliability. You don't get noise loss like you would in electrical signals. So there is loss. There is needs to repeat things and improve the light, but what light travels from I'm in Taiwan to India to San Francisco in a millisecond. right? What's the speed of light? Once it's on the wire, now the question is all the devices in between. But for example, I'll give you a good example of this, the fiber. There are companies now laying fiber directly from places like Australia, Western Australia, where they have great energy resources, direct to data centers in California. Because it's cheaper to run data centers in Australia than it is in California because of electricity prices. So if you think about, well, now there's a latency, there's a delay, but they're going data center to data center and actually computer to computer. So there's very, very little, delay that's caused by these because we're running end to end at the speed, and we're not going fiber to Ethernet. And then, by the other way, the old days we used to go fiber to we go Ethernet to fiber, then we go to a router. We get to a great, Cisco router, and then we convert that back to electrical, and then Cisco routes it for us, and then creates electrical, and then sends it back to us. So we've gotten all this. Now they're going to all optical switches. So there's two ways of doing that. One is with light guides, where they actually have this little path that runs around. And then they're doing it with mirrors. So mirrors are deployed today. And so very fast, because a lot of these networks are fixed. So example is the one that goes between Brisbane to LA, Los Angeles. That whole path is fixed. And only in an emergency would that change. So the mirrors are all, the mirrors can move, but they don't need to move. The whole path is fixed. There's one path for transmit and there's one path for receive. So now the world is smaller. Now the world we can do things like the metaverse. We can do things like high-end video conferencing with high definition up to 8K. So, and when you get into this new three-dimensional multi-camera streaming that's coming now. Google has announced a product that has almost like 6 cameras that are put together, compressed, and then is sent at light speed to the other side. So humans can accept up to 300 millisecond delay. That's 300,000 or 300ths of a second delay. Your brain can't process anything more than that. So long as we keep the delay below that, we think we're talking in real time. We're not.
That's true. And in fact, also let's kind of step back. So when you talk of this photonic chips or other areas, how different is it from a traditional digital logic chip? Can you walk us through in terms from a layman's term or simple terms? What are the kind of blocks of this whole ecosystem?
Yeah, I'll try not to get too technical because in the regular chips, we have and OR gates and NAND gates. So we actually have that in optical too. So there are AND gates and OR gates. It's basically inside the light that we run these little paths through and then they can then split the signal between AND and OR, and they can do the same thing as a regular chip does, but it's bigger. So there's a lot of work to squeeze it down. That's why we're currently, as what you're speaking of is inside a router. This is using what we call light guide. But if we're talking about inside a chip, so yes, we do have. Well, it's not inside. It's inside a big chip. Inside that chip are chiplets, which are like we think of chips, CPUs and memory, HBM memory, and all. And now in our day, we had CPU, we had a GPU card somewhere, and then we had memory, and then we had a hard drive. Now that memory and that GPU and that CPU are all in one chip now. That's what the NVIDIA, the ironwood from Google, Amazon is building one, Meta is building one. So they're putting it all together. Now, the next version of this in a few years is called neuromorphic computing, and that is an optical chip. So there are big versions of this right now because of size. But what we're trying to do is get light to be the size of a pixel or smaller, Pixel is actually pretty big, so it'd be probably somewhere in the submicron level, but you need a so then we use this routing, this sort of circles and movement of light, because light can be split, and it's still the same power. But if you split it, sometimes if you lose power, you can read that. So then you get a reading when the power is split. You can get a reading when the power is full. You can merge it back, two signals back later, and then that gives you another reading. So that area is coming. That's been around for 10 years, and it's got probably another 6 or 7 years before it becomes commercial. But yeah, so we're going to see light everywhere. Why? Because electrons cause heat and takes up a lot of energy. So electricity, anything that needs electricity, and by the way, photonics need electricity to start, but we don't want to have electricity all the way through. So if we can just start with a little bit of electricity, create that, and then get it out on the wire, and then we can then create. Now, why? Why don't you just keep electrons? Well, because photons can act like neurons. So a neuron is what's inside your brain that flashes back and forth. And what is a neuron? There's a transmitter and a receiver. Okay? So if I can simulate that in light, then I can simulate your brain. If I can simulate your brain, then I can think faster, because your brain thinks 10 times faster or 100 times, I forgot the number, faster than the best computer today. And you run on 1/10 of the energy or 1/20, I forgot. You use milliwatts compared to gigawatts for a computer to run your brain. So our goal in computing is to get to being the fastest thing, as fast as a human, and at the energy level that a human does. And that's the 2030, 2060 road that we want to get to. And it takes one step at a time. And so, yeah, we have electrons today, and then we're slowly going to lasers, photonics, and eventually we will run our world on photons. I may not be here, but it'll run on photons.
Yeah. So in your view, I think one can expect something on this commercially in the next 10 years. Is that a fair assessment?
So CPO, co-packaged optics, is here. TSMC is invested heavily. Samsung is investing. So they are working on that now, and they have what they call CoWoS, chip on wafer on silicon, which is basically putting chips down. You're basically creating a computer on another piece of silicon. So I'm basically, in our day, or even today, you buy a motherboard and then you put the chips on top of that motherboard. Well, what if I just put everything in one big chip? That's why when you see the NVIDIA chip, it's huge. That's because that's a computer. It's not a chip. It's a computer. And so that having fiber coming out is coming, and it's in testing. It'll be in production in 26, 27. And there are already all optical switches out there. So those are all here. They're just not in mass production because data centers takes years to. You gotta expense all of your existing equipment till there's no value in it, and from accounting point of view, and then you can go to something else. But we're also waiting for the CPUs to go. If you look at the NVIDIA Rubin, it's 10 times what the Blackwell was or is. So, maybe something else is coming. So if we wait just a little bit longer, and we use our Hopper CPUs, we can go a little bit longer. So that's the big problem, but it's coming, and CPO is here.
Yeah. So one of the fascinating aspects of what you explained is the whole savings on power and cooling, right? And specifically, if we kind of make a slight diversion on the whole topic of AI, because when you talk of AI, one of the key artificial or artificial or super intelligence, as many people like to call, but the underlying hardware, the whole data center cooling, power consumptions, that really is a big problem, right? In many
So,
places they talk in percentage of the country's power requirements, right? So it's a tough thing. So in this whole era of photonics of chips, which you just described, I think a lot of these inherent foundational roadblocks or foundational problems what we face right now will no longer be there. And I think also the way to look at hardware is would be different. You just gave an example of how you won't have a motherboard and everything because everything is kind of integrated. Seeing into the crystal ball, what's your prediction on how this kind of will help in the whole AI and overall hardware ecosystem?
all right. So let's look at AI in 2030. What does that look like? So we're going to probably have robots. Okay. So we're 2026. We will probably have some kind of robots running around. They require very low latency. So first thing that'll come is an edge computer that robot can talk to. That edge computer can be at your home. It can be in the small cell, the telco side, but you're going to try to cut and have as little latency. So you might be running your AI in your home. And that's something I firmly believe that we'll all be running AI in a private network. If you know Claude Code, not Claude Code, but OpenClaw, that's going crazy now. I'm a big user of Claude, OpenClaw, and yes, it does a lot of things for me, but it's running from my house. So we're going to start to see, but if I'm going to get I'm doing 4K video, if I'm doing a robot in my house, if my kitchen is online to Amazon, if my closet is online to I have a iStyle, which is a fashion it's a assistance company called it. She helps me decide what to wear. The app. So I have all that data now. And as we're running on all of this, where are those decisions made? Where's the privacy? That's all going to start moving to the edge. And so we're going to have a lot more compute power within the home. So that's why the price of these very expensive chips, they're making what they call inference versions, which are the smaller versions, and those will sit in my home. And if we start looking down the world, everybody, I visit India and lived in India. Now every taxi driver has a smartphone. In China, everybody has a smartphone. You need it in China if you're going to pay for anything. So everybody's consuming this bandwidth. And we start looking where AI is. AI is to this generation what HTML was to the previous generation, meaning it's everywhere. It's Bluetooth. It's in every device. The question is what's the value of it? What can it help me do? What does Bluetooth help you with? What does HTML help you with? So as you start to think about everything that it can do, but AI is what? AI is very simple. It's data. What is data? Data is sensors or it's existing information. So Wikipedia is the existing information, but my heart rates and my body capturing all my body information, that's me and it's local, and I don't want anybody else to see that data. So yes, AI is moving into your home as a core. This is OpenClaw has already proved this. But OpenClaw is not for the mass market yet. It's probably 2 years to 3 years, and which matches what we say AGI is coming. We say AGI is 2030, 2029, 2030, and truly mass production of AI, of AGI, artificial general intelligence, where the system is as smart or smarter than me, and that's really easy to do. that is now, coming into the system. I mean, if you look at where Claude is, 4.6 inside of Excel, inside of PowerPoint, and Gemini inside of my email, it's starting to do things for me. It's starting to remind me and helping me plan my trips. I can tell it, hey, I'd like to go to Bangkok for the weekend, and the AI agents, agentic AI. So we started out with just LLMs, and then we went from LLMs to simple agents. Now we're doing multi-agents. And this is something we predicted in 2018 that multi-agents would come. So multi-agents are here today. Next, from there, we're going to physical AI. And physical AI is robotics, it is automation. So multi-agents will be in my computer, in my phone, in my life, in my robots. So that is basically, I would give it a simple, hey, I want to go to Bangkok, book my hotel. But you know what kind of hotel? First question it's going to ask me, is this business or pleasure? This is business. Okay, business, we choose different hotel. Somebody else is paying, right? So we choose that. Then we choose the airline. Oh, by the way, it knows my airlines. It knows I like to sit at 23G. If it's a 777, I sit at 23G. If it's a smaller, so it knows all these things about me from my history, or it asks me questions, or it looks at my past. So for example, I personally am what it's called quantified selfer. I collect data on my life for the last 15 years, almost every day. I know my weight, I know my blood pressure, I have my own EKG machine, EEG for my brain focus, and I just recently got a cholesterol device. And so I collect all my data, and I take a lot of supplements. And then I have, of course, I'm old, so I need my heart pills. So the question isn't, do I need this medicine? It's what time of day should I take it? Remind me to take it. Verify that I took it. I don't want an app that goes, please take your pill, and I got to press a button. The system's got to know. It's got to understand me. This is where, this agentic AI with sensors and cameras and all come in. So, someone is going to build the world's next cool pill dispenser. Please do. So that it knows when I took my pills and knows what time, and it reminds me, and it's multiple pills, and it automatically reorders my pills for me. So, which reminds me, I got to do that later. All of that stuff is where we want to be in life. Humans are naturally lazy and that's why we do automation. That's why we try to focus. I mean, you can say that I love to go outdoors and I love to go hiking, but you still need that GPS. So you still need the tech. But the tech and AI for hiking is here, right? So there are a lot of apps out there that help you go hiking. I don't use them. But there's a lot of that kind of technology here today. So it's going to help us improve our lives. You can ask me what we're going to do with all the free time.
That's another challenge. But coming back to the point of, so essentially, the way I understand it, the whole photonics-based ecosystem, hardware, etc., would become a foundational requirement for this new era we are entering into of ultra-low latency, robotics, etc. Right?
Yeah, because everything we talked about was low latency. Right? You don't want your robot it needs a menu. It could take 2 seconds, that's okay, but it can't take 20 seconds. We won't accept that anymore. We used to, when we did a file transfer, we used to take, a few hours, and we were acceptable to that. I have dual fiber to my home with a load balancer. I don't accept any of that anymore. Oh. I want something here now. I want it now. I want no errors. And you can't have lost packets in your robot, because if your robot is downloading a new learning system, and it fails, well, does it recover, or does your home crash? All right, but let's go back to the one question you asked me, which I didn't answer, was power. So, as you know, I changed careers for a while and focused on energy problem from device all the way to city to batteries, and I ended up focusing my energy on batteries. and also in hydrogen in hydrogen and well. So what is the problem? The problem is, and because I went from data centers to energy. Why? Because I realized that the data center's biggest problem was energy. And even if they go to a low power device, that whole energy requirement today, 1 gigawatt, which is where people want data centers to be, is about 800,000 homes. Okay, about close to 1 million homes. So if you take a place like Liverpool, which has 800,000 people, that's a data center. So how do we store energy? How do we generate energy? And how do we save and store and predict? So my work was in prediction. So understanding where clouds come. So everybody loves solar, but the problem is in solar that if the cloud comes over, you might lose 10-12% of your energy. Well, are you planning for that? Did the grid prepare for that? This is the problem in Spain had. So when energy is not understood fully and not managed fully, you get blackouts. So how much did the Spain blackout cost? A few $1 billion. In Taiwan, it's more because if TSMC goes down, it's $100,000 per wafer. So $30,000 a wafer.
True. So yes. So in the photonics world, wherein the power consumption is less, we'll have less of such challenges as well.
I wouldn't say less challenges. Yes, it will consume less, but we're going to have more devices.
Yes. Classical problem, right? You build a huge network of roads, hope that there won't be any traffic jams, but then you have got to fill the roads. Yeah, but
I mean, come on. I as you know, I lived in Mumbai, and when they opened the Pune Mumbai, it was empty for the first, and then suddenly everybody was on it, and it became a traffic jam.
True.
Right? So yeah, you went from like during the testing, it was like very few people on it, and then it went crazy, and now it's a traffic jam on holidays, right?
True. So that's the human challenge, right? We solve current problems, and those solutions create some new problems for the future. Thanks, Bruce. This gives a great perspective, and thanks, dear listeners, for tuning in. To subscribe, share.
Yeah, thank you guys for listening. I can ramble for hours, but what you just mentioned was this is what humans do, right? We create one problem, we solve it, and then we create another problem.
Exactly. And dear listeners, give a podcast a 5-star rating if you like the content. Bye for now. Talk to you soon.